Hello, Chem 111. This video answers the question, how can you tell if two Lewis structures are resonance structures of each other versus just different ways of drawing the molecule? So I'm going to start with the example that raises this question for people. So if you look here at the top example, this is the molecule ozone, O3, and these are two structures of it, and they are actually resonance structures. And so we would draw a resonance arrow between them. The bottom example here, HCN, these are not resonance structures. In fact, this is just the same molecule flipped on the page. So the confusion sometimes comes from the fact that if you look at the ozone structure, you could actually flip that as well and get the second structure. So I'm going to teach you two ways to think about this so that you can understand when something is a resonance structure. So the first way to think about this that I'm going to give you is a very practical answer to the question. And that answer is, you ask yourself this question: can you leave the skeleton, and by skeleton I mean the single bonds, of one structure on the page and get the second structure by moving only lone pairs, which I abbreviate LP, and or double or triple bonds, so bonds that are on top of the single bond, they're not part of the structure. So if your answer is yes, I can do that, then it's a resonance structure. And if the answer is no, I can't do that, then it's not a resonance structure. It's very simple. This is a practical explanation, so I'll walk you through it with this one. If I look at the top example, I can take my first picture and I can leave everything where it is on the page, and I can move that double bond there, and I can move this double bond here. And when I do that, I end up with this structure, right? I didn't have to move any atoms. All I had to do was move lone pairs and double bonds, and I can get the structure on the right. I do want to make one little caveat here, which, depending how you've chosen to draw it, maybe you move the molecule around the page a little bit in a different way, and you'll see this in the example I give you at the end. But the key is you have to leave the skeleton intact. So those single bonds, which I'm going to circle here, so this is skeleton, and I left those intact. So that's a resonance structure. All right, if we look at the bottom case then, there's nothing I can do, right? So my N is here, and now my N is over here. I can't change this just by not changing the skeleton. In fact, I could just flip the whole thing around, but I can't get two different pictures just by moving double bonds and lone pairs. So this one is not a resonance structure. Okay. So this is really helpful as a first pass. If you're not sure if something's a resonance structure, can you get it just by moving around those lone pairs, double bonds, sometimes triple bonds? Okay, so that's the practical explanation. There's also what I call the underlying reason, which is actually more important. So the underlying reason why we call something a resonance structure is as follows. The resonance structure, or the resonance structures, in this case the second resonance structure, is required to describe bonding in the molecule. And so to see this, what I recommend you do is describe the bonding to someone who can't see it. And in doing this description, you really can't use things like left and right because molecules move in space. So molecules don't care what your left and your right is. So let's talk about ozone. So when I look at those two resonance structures, and I can use the practical rule to decide they are resonance structures, if I describe the bonding, I would say, well, I have 3 oxygens, and the central O is connected to the outer 2, outer with an R, outer 2, by something that is a sort of a combination of a single and double bond. That's what the resonance structure is telling us. It's telling us that's not a single bond, it's not a double bond, it's a combination of the two. And it's just important to note this is different than either structure alone. So if I look just at one structure, so if I say, okay, I'm going to look just at this one on the left, this one would be O bonded to one oxygen with a double bond and to the other O with a single bond. That's what I would say if I had just one structure, and it's important to note that this is incorrect because there is a resonance structure and you need it to describe the bonding correctly. If I describe the bonding in HCN, I would describe that as carbon in the middle. Middle is okay because it describes connectivity. It's just left and right are kind of useless. Carbon in the middle, it's single bonded to a hydrogen, and it's triple bonded to a nitrogen. That's an N. And either picture I look at, that's true. It doesn't matter that the nitrogen's on the left one place. Everything else is the same about those molecules. All right, so we're going to end with a problem due. So here's the problem, and I encourage you to stop the video at this point, and then you can continue playing it, and I will give you my explanation. Each of these pairs, A, B, C, and D, should be labeled. They're either two resonance structures, in which case you should go ahead and draw a resonance arrow between them, or they're the same molecule just drawn differently on the page. That's like what HCN was. Or there's another option. They're totally different molecules. And we didn't see that before, but I think you can figure that one out. All right, so stop the video, and when you're ready, come back and try these, and then you can hear my explanation. Okay, so A, the question is, can I get this picture here just by moving the non-skeleton electrons on the left? I can't. Because it's actually been flipped around. So, all right, so if I flip this one around, is it just the same molecule? And here's where the description is helpful. I would describe this as C double bonded to N, double bonded to S, and I would describe either one as that. So this one it's just the same molecule. Option 2, because I don't need a different description for either one. So that's A, same molecule. All right, so if we look at B, here the atoms are in the same order on the page. The skeleton looks the same. So the question now is, can I get to the second picture by moving electrons on the first? Indeed, I can. It would go something like this. And so in fact, these are resonance structures. Option 1. Okay. Now, option number C, or letter C, is a little different. What's different here is that actually the skeleton is completely different. So the skeleton is different. And that means it's a different molecule. So over here, I have a central carbon bonded to sulfur and nitrogen, just in case you haven't figured this out by now. The ones on the left are all the same. And here I have a nitrogen as the central atom. So in fact, these are just completely different molecules. Different skeleton is different molecules. That's option 3. And a little new piece of information is that when you have the same chemical formula, but a different skeleton, that's an isomer. Okay, so D is the trickiest one. Can you get to the molecule on the right by just moving electrons on the left? And the answer is like, yes, you first have to rotate it. So you're allowed to do that because molecules rotate in space. So I could just rotate this in space, think about it doing this kind of thing. And I would end up with, and double bonded to carbon, double bonded to sulfur with the lone pairs all where they should be. And now that I've just moved it around the page, now in fact, this is actually like the second one, like B, right? I could move these electrons in here, these electrons in here, and in fact, those are resonance structures. So it's okay to say, these are resonance structures. When we draw them, we typically leave the atoms on the page so as not to confuse ourselves. But so this one, these again are resonance structures.